move you forward. It's mean. Okay. There we go. All right, so that should be recording now. Okay. All right. Grand Central Dispatch, aka legacy concurrency. I am teaching you this not because you should necessarily be using it, but because it's very helpful to know and understand kind of how Swift has done things in the past and why it has moved to the current concurrency solution. You will also, if you ever do native iOS development, probably run into a lot of things that use Grand Central Dispatch, legacy code that is using the old way of doing concurrency, the old dangerous way of doing concurrency, okay? So let's talk about threads. Really? It's not gonna come in lines, whatever. All right, so threads are code that run quote unquote simultaneously, okay? So if you want your code to execute two things at the same time, if you want to say, I don't know, display an animation on the screen while also downloading other animations to display in the background, that's concurrency. That's something that you want to run at the same time, okay? So in theory, it runs at the same time. The reality is a little bit more complicated. It has to do with how many cores your processor has. It has to do with what the runtime considers to be important, what the priorities of the different pieces of code are. And basically, it does this kind of constantly like each thread kind of is like, it's your turn. Yeah, I'm not doing anything. You can take over. It's good. And then the next one's like, oh, cool, thanks. Yeah, I'll run like 3 lines of code and then I'll pass it back to you, my man, right? And then so on and so forth, right? So they just ping pong back and forth, and it ends up still being kind of serial, but it's happening so fast that to us, silly humans who see things in 120 FPS or whatever, we can't really tell the difference between simultaneous and very, very fast serial. So the other thing to note is that kind of process I talked about where the threads are kind of yielding and passing back and forth to each other. If you have too many threads doing that too frequently, you get what's called thrashing in the CPU, and it's just basically flailing around and not getting anything done. Essentially you just kind of break the computer for a little bit. Not permanently, but for a little bit. So you want to avoid having too many active threads. So let's look a little bit more at the theory behind threads. So here we have our core. Let's talk about a situation where we just have the one computer core, okay? And we're going to do normal kind of parallel code. This is kind of what I described, right? So here we have 2 different pieces of code that, to us, we have defined them to run in parallel. They are concurrent. They will run at the same time to our perception, right? But what we know as programmers who are smart and know these things, we know that they're really not going to run at the same exact time. They're going to run kind of at the same time on one core, and they'll just do it really, really quickly, so we won't notice, right? So our runtime is going to look at this and in the most basic way that you could do this, you could say, oh, okay, these 2 pieces of parallel code, they are equally important. I'm just going to have the core execute them back and forth, just ping pong back and forth between each line of code that I'm supposed to execute, right? So first it will send code A line 1 to the core. Oh no. My animations are messed up. Don't look at them. The serial thing shouldn't reprint every time. It should just stay. And I think the arrow did a weird wobble. That was weird. Anyway, so then we print code B line 1, right? Oh, that's really annoying. And then we'll do code A line 2. That's what I get for making a change right before lecture without double testing it. Then code B line 2, code A line 3, and code B line 3, right? So now we have this kind of execution, and this is how the code runs on the computer, or in the core, the CPU of your computer, right? If it only has one core, this is what happens, right? So let's think about what happens if we have 2 cores, okay? Because modern computers tend to have more than one core, right? They'll have 8 or 16 or 8 plus 24 virtual cores or whatever they say nowadays, right? But the reality is that you can now actually run code simultaneously. What was once a pipe dream back in the 70s is now reality for you. Congratulations! Welcome to SIG-aborts and execution errors and all sorts of problems that come with concurrency that we'll talk about. But for now, we can talk about the concept of threads. So before we were talking about cores, now we'll talk about threads. Threads are an abstraction that exists on pretty much every kind of computing hardware now. Windows uses threads or something like threads, and Mac uses threads, and iOS uses threads, and they all use threads. And threads are kind of intended to be sort of this single, set of things that kind of run, one after the other, right, within that thread. And then the thread is the thing that's doing that back and forth yielding, right, process, okay? However, if you have 2 cores and 2 threads, then you don't need to pass back and forth. You can just run at the same time. Ooh, right? These pieces of code execute simultaneously because they're running on 2 separate cores at the exact same time. Very cool. Technically not true, but it's close enough to true, and it's much closer to true than the previous assumption. So, it is what it is, right? So this is conceptual, right? So now it runs at the same time. That's great. What if you have more threads than you have cores, right? Well, then you have to get something called a scheduler involved. So before we talked about like a kind of simple implementation where we have 2 pieces of concurrent code and 1 core, and it'll just ping pong back and forth between the pieces of concurrent code. Here we're going to say, okay, so we have this special piece of code called a scheduler, right? That tends to be hard-coded into the chip, right? And its job is to make sure that the threads are running correctly. It keeps track of things like priority and how long has it been since that thread got run, and all sorts of esoteric nonsense that you don't need to know because you're just using it, right? But essentially, it makes decisions about who should be getting to run their code next, okay? So here, the scheduler has decided thread 1 gets to run its next line of code next. So we have these 2 different pieces of, we have these 2 different kind of execution stacks, if you will, for each thread. And so this execution stack is green because scheduler says go. Green means go, right? And red means stop. Oh, there we go. Okay. Red means stop. So thread 2 is not doing anything right now, right? So this 1 core is getting code A line 1, right? So it passes on, and then the scheduler is still saying, you know what, thread 1 is still more important. We're still going to continue executing thread 1. Nope, that's not true. I just messed up my animations. Sorry. So now the scheduler says, okay, actually thread 2 just gained priority. It got a bunch of new data in from the network, and that bumps it up in our estimation, so we're going to run the code there now, right? So thread 2 now goes, and it executes its next line. At this point, the scheduler continues to say, yeah, thread 2 is the important, it's the big cheese. It's the head honcho. It needs to be running right now. Until all of a sudden, once again, something changes. And thread 1 is now the big cheese, okay? So thread 1's going to go, and it's going to pass its stuff down and run that in the core, right? And it will finish. And now it doesn't have any more work to do, which means thread 2 gets to finish what it was doing, right? And so because there's no other threads in this beautiful, amazing, sanitized world that we've created, the reality is your computer's CPU is running many, many threads all the time, right? And so this scheduler has a lot of work cut out for it, right? So you've got thread 2, code B line 3, passes in, right? And now that executes. And now the scheduler's like, there's no work. We can just go idle, reduce the voltage on the CPU and wait for more work to come in. Never happens, but it's possible, right? So that's the theory. Yeah. If the code errors out, then that thread crashes. It depends on the kind of crash, right? But basically, if you have an error on like code B line 2, then this thread just cancels, right? It stops sending work, right? And the scheduler is the one that kind of cancels it. Or in this kind of sanitized version, it might not be a scheduler. There might be something separate that's keeping track of if it's still running or not, that sort of thing, right? But basically, if a line of code crashes, then the thread will crash as well, right? And then if the threads are both a part of the same program, then all the threads will crash, right? If they're considered to be the same. And that's a safety feature that the computer employs. And that's also not true in every language, in every computer programming language, but it's true in Swift. So if one of your threads crashes, your whole program crashes, right? I think JavaScript just keeps going if it crashes, which is just wild to me, but whatever. Cool. All right, so queues. Queues are a library that Apple created that abstract threads and parallel work. Basically, Apple looked at threads and they saw all the things that happen when you try to use threads and don't really understand how they work and only have the understanding that I just told you, right? Which is kind of really high level and not super useful if you're actually like programming and trying to write your own scheduler for the threads in your code, right? So Apple created this thing called queues, dispatch queues, right? And it's a library that Apple made to abstract threads and parallel work. Queues follow a FIFO pattern because they are a queue, so first in, first out, right? It's just a line, right? A queue waiting for your movie tickets or whatever. Do people still go to movies? No, I'm old. So it follows that pattern for scheduled work. Queues can be serial or concurrent. Serial queues keep using the same thread. They just execute in line. Rather than having each of those blocks that you saw be lines of code, they are instead discrete sets of code that you schedule to work in the queue. And if you'll recall, we have a very specific way to pass around discrete sets of code in Swift. Closures, right? So you'll be seeing a lot of those. Concurrent queues spawn new threads as needed. And this as needed thing is pretty important. This is a big part of why you use queues and dispatch. Basically, it has a thread pool, so it keeps a bunch of threads alive all the time, like 10, right? And if any are not being used, it grabs one of them and says, oh, okay, run on this thread, right? And in that way, you're not constantly starting and stopping threads, right? However, if you spawn too many threads, more than the pool has, then it has to instantiate more and more threads, and you still can get CPU thrashing. So, and then there's only one main queue, which runs serially. So basically, there are all these different queues that you can create, and they all have threads. And then there's considered to be one thread that's the main thread, and the only queue that accesses that is the main queue. And everything that runs on main has to run serially. And that will be very important to understand when we start to look at creating views and stuff for our iPhones, which is going to be basically class after next. UIKit and Swift UI, whenever you're trying to draw UI to the screen, Apple requires that any work you do to draw must be done on the main thread. And they do that as a safety precaution because if you don't do it that way, stuff can get really weird really fast. And they want to make sure that apps on their phones are best in class, and so they make that requirement as a part of the compiler. Okay, so let's actually look at code. This is the library dispatch. So first thing to know is the sleep function. Sleep pauses whatever thread you're currently executing on for the number of seconds that you pass in. So here we have a print first reminder that will print the first reminder string. Then we have the sleep. It will, after 1 second, print the second reminder. Then we have sleep again, and after 1 second, it will print the last reminder. So basically, you have these pauses in execution. So if you do this in the terminal, you will see first reminder, then something that feels like more than 1 second to you probably, and then second reminder. And this is how you can kind of delay things, right? So dispatch queues are basically a type that Apple has created that you can instantiate, like we have here, and you can pass it a label. They prefer you to use this kind of com.blah, blah, blah, this reverse URL syntax for the label. You don't have to. You can call it whatever you want. But they like to say, oh, there's so many queues running at the same time. Debugging is easier if you do com dot your company name here dot your app name here or whatever, right? As long as it's something you can recognize, it's not a big deal. So then you can call this async function on queue, and it takes in a closure. So it takes in as its only parameter a trailing closure, And so you can pass it this closure print second reminder. And then after that, you can print the last reminder. And then because I'm doing this in the main like .swift file or in a playground, I have to do this runloop.main.run in order to keep execution going. Otherwise, the program exits before second reminder ever gets printed, right? So if you ever see this, that just means I'm just catching it at the end and telling it, just wait, for whatever. And then it'll run forever unless you kill it. So you do have to kill it. But okay, so because we've done it this way, right? First, we print first reminder, great. Then we queue this asynchronous code and we put it on the queue and we say, hey, dispatch queue that I have created, my friend, whenever you get a moment, please run this code, right? And then we continue along the main thread to execute and we say print last reminder, right? So last reminder gets printed in this case before second reminder. Something to note, just by putting something into the queue, by calling queue.async, you create this closure, you put this closure into the queue, and then it gets scheduled onto the queue. And so the queue is constantly executing. You do not need to call queue.run. You do not need to tell it, hey, queue, I want you to please start. The queue is always running, right? It's always going. So here we can look at threads. So basically you can do this thing called thread.current, right? Which is just it's a static computed property on the thread type, right? So you can just call thread.current and it prints out this kind of lovely jargon here, right? But this is helpful to know and see what thread you're on, right? This here is the main thread. This hex code is basically its location in memory, kind of, sort of. Don't worry too much about it. It's a unique identifier. But like you can see here, the name is main, right? Oh, this is the main thread. It's special. It's really cool, right? And then here, the name is null. This one doesn't have a name. It's gross and weird, and it's not main. And it's also got the number 2. This is the second thread that our program is running, right? So here we've created and used 2 threads. You always create the main thread whenever you run code. And then we've made our own second thread to run on. How exciting. So let's take a look at this. Basically, you can queue multiple things, right? So here we put 2 different closures into the queue, right? Second reminder, third reminder, right? And then within them, we also sleep, right? And the interesting thing about the sleep function is that it actually kind of puts the whole thread to sleep that's running, right? So these, because it's a queue, right, and it runs in a first in, first out fashion, okay, the first closure here that prints second reminder is going to execute first because it was the first one placed in, and then it will pause the thread for 3 seconds. And then it will print second reminder. After that, the queue will then say, oh, cool, I also have this other thing that was added in, right, by the main thread while you were sleeping, right? And this other thing now wants to run. So it runs, and it sleeps for 2 seconds. And then it prints third reminder, okay? And you'll note that even though we have 2 different closures here that we are putting asynchronously onto the queue, they are both running on the same thread number 2, right? So we go through here, we run through all this, we kick these 2 things off, and then we print last reminder, and then we just wait to see what happens. That's what this run loop main.run is, right? So then after 3 seconds, we print second reminder, and after 2 seconds, we print third reminder. And they're both on the same thread. Yes?
Does the queue run immediately after it gets its first it gets the second reminder?
Does the queue run immediately after it gets the second reminder? Yes, the queue is always running. Always. It's just looping constantly, just like main is.
So it first goes to sleep. So when does the third reminder gets put in?
Third reminder gets put in because it's happening on the main thread, and the main thread is kind of executing. This doesn't actually run. This closure, the first closure, the second reminder closure, doesn't run until we get to runloop.main.run. It doesn't kick off immediately. It's not fast enough, right? But if it was fast enough, right, then the thread is put to sleep, but the queue continues to accept new things in, right? So the queue is managing a thread, right? It is not itself the thread. So it's scheduling work to put onto the thread, right? So it keeps track of the order of things that need to run next for the thread and not actually putting them on until it's time for them to go onto the thread.
Okay, so if I were to declare another Q2, that's not another thread, it's just another queue that can spin up a third or fourth thread.
Yes, and you'll find that it will. It does. Every queue does manage its own thread or set of threads. Yeah. So if you made a Q2 and put this second one on it, then they would run concurrently, right? Which will actually, I think the next slide or the one after that will show it. So, but we're also going to look at something called async await, async after, not async await. So you can also, instead of calling async, call async after, and you give it a deadline. You use this .now plus syntax. It's weird, but it's in seconds. So it's just the current execution time in seconds, and then you add 3. So this is saying, hey, put this into the queue after 3 seconds. So it doesn't actually schedule it to the queue until after that time has passed. So you're saying, cool, here, have a closure, but don't put it in the queue yet. Put it in the queue in 3 seconds. This messes with our FIFO stuff, first in, first out, because it's a queue. So here we're saying, cool, second reminder, we're going to add it to the queue after 3 seconds. Then here we say, cool, this third reminder print, we're going to add it to the queue after 2 seconds, okay? And because we're adding it after 2 seconds, it goes into the queue before second reminder does, right? Because it's not getting added to the queue yet. We're holding it in stasis and waiting until that amount of time has passed, and then we add it. We're scheduling it to be added, which is very similar to how the queue schedules the things in the queue to be added to the thread. It's like another layer of waiting, right? So we'll see here that we've created async after, deadline now, +2 here, right? And then we run after 2 seconds, we get the third reminder here, right? And this is on thread 2. Then we only see this after 1 second, we see second reminder get printed, right? Now this might make this look like it's running concurrently. It's not. It's a trick. It's dirty and deceitful, okay? This is not running concurrently. It's just because we've called async after deadline, we are not scheduling it to be run until 3 seconds from now has passed. From whatever the time when that line of code executes has passed, 3 seconds later, then it gets added to the queue as if you had called queue.async, okay? So when you add something to the queue, it will run as soon as it can, right? In this case, because it's after 3 seconds from now, and this is after 2 seconds from now, and these run pretty much instantly, third reminder will run after 2 seconds, and second reminder will run after 3 seconds from the start of, from this kind of middle point of execution. And this is all going to print pretty much simultaneously to you, to your perception, right? So this will look like it's running at the same time, but it's not. It's just running after 3 seconds have passed. Does that make sense? It's kind of fiddly. Okay, cool. So that's async after. Now we're going to look at concurrent queues. So this is where queues can start to make new threads and manage more threads, and you can start to get into trouble. This is where you actually have things running at the same time. Remember how sleep pauses whatever thread is currently executing on? That means that, you know, if these are both on the same thread, then this will sleep for 3, print this, and then this will sleep for 2 and print this, and that's the order that it goes in because it's a queue. So it's the first in, first out. So first, second, then this one, and then this one, right? If you make the queue concurrent by adding this attributes.concurrent little thing here, this kind of setting for the queue, then they will run at the same time on different threads, okay? So now you get a very similar result to the last one, but these two pieces of code are in fact executing at the exact same time. And because this first piece of code is still executing when we schedule this second piece of code, because it's sleeping, right? It put the thread to sleep. So the queue looks at the thread and says, okay, I want to schedule this to the thread. Oh, I can't. There's something else is running on it. But I'm concurrent, so I need to make sure it's always running. So thread pool, give me a new thread, right? I'm going to put it on that, right? And then those threads run simultaneously, okay? So these two pieces of code are in fact executing at the same time, even though you get the exact same result as here. Except for one thing, of course, the thread is different. So the second reminder prints later on a different thread. Okay, any questions about concurrent queues?
Number 2 and 3, they are the child of the main thread, right? So is there
Yep.
any limitation for the number of threads under the main thread?
So the question was, are thread number 2 and 3, they're the children of the main thread. Is there any limitation to how many threads the main thread can spawn? No, which is dangerous. So be careful. That's what I'll say. Yeah, it tries to limit it as much as it can by using a thread pool, right? But you can do some weird stuff with it, and I'll show you actually in one of these slides. You can also combine that async after deadline with concurrent queues, and you can get some weird, funky, fun results. I'm going to leave this to the reader. We're not going to walk through it right now because it's not super important. We're not going to be using this library, but it's good to know how it works. But basically, it's very similar to the same results as before. It's just behaving a little bit differently because the deadline is saying, hey, go ahead and run any time after this point in time happens. So anytime after, meaning if something else is still running on it, it can be scheduled later than whatever that time is. You're not saying, please do this immediately at that time. You're saying, do it at some time after that. Okay. So here's the main queue. Let's talk about that. So this is how you access the main thread, either that or by running in the main.swift file. Everything that runs in main.swift is on the main thread by default, okay? So you can print the first reminder thread current to see that we're on the main thread. You can do this dispatch queue.main.async. Dispatch queue.main is a way to access the main dispatch queue, okay? And then you can schedule async things on it. Do not call dispatch queue.main.sync. You can technically schedule synchronous code onto a queue for some, I know why, there's reasons, it's not important and it's not relevant for concurrency, but if you call that, you'll crash, so don't do that. On the main queue, you'll crash, so don't do that. But the main queue is by definition serial, it is not concurrent, okay? It cannot be concurrent, it's just one thread, and it's the main thread, and it just runs in order that it receives the things to run. So after 3 seconds, we print second reminder. After 2 seconds, we print third reminder. Cool. Any questions about the main thread? So we have also this kind of cool little syntax here called dispatchqueue.global function call .async, okay? So here, dispatchqueue.global returns a brand new dispatch queue. You can specify a priority, or it can be of the default priority if you don't specify a priority, but it creates a new queue and it gives it back to you, and then you can immediately call .async on it. In this case, we have created 2 different queues. We are doing this on 2 different queues. As a result, we end up on 2 different threads. Queues returned in this way are by default concurrent. They are not serial. Cool. Any questions about dispatch queue global? All right. So you can also reuse dispatch queues inside of functions, right? So here we have this dispatch queue.main.async after, blah, blah, blah. So we're going to pass in a time that's going to be our, after deadline, and then we're going to print this time and message thing, right? Basically, you can use it inside of functions. You don't have to use it in the global scope. You can use it wherever you want, right? That's executing. You can't use it where you would define properties or something like that. You can't use it in a protocol definition, right? But anywhere that's executing code, you can use dispatch queue. Yeah, so you can just reuse it. When you reuse this, because this is main, you are still reusing the same dispatch queue. If you were calling dispatch queue.global, it would still make a brand new queue every time, right? Which is not very performant. If you want to do something like this, you really should create your own dispatch queue like we saw in the very first slides and reuse them that way if you need concurrent code. Okay, so dispatch with closures. This is how concurrency has been done in Swift since its inception until Apple started to change things at the language level about 4 years ago, okay? So basically, there is a problem, which is getting results from slow blocking code. If you were to make a network request, those tend to take a long time. Long time meaning 1 to 5 seconds, right? That's a long time in computing. If you do that on the main thread and you're doing a little spinner animation, then your spinner freezes. We've all seen that happen. It's no good. It makes us, as people using the application, feel bad. And the last thing you want to do is make your users feel bad. So what do? Well, you take that network code, you wrap it up inside of a dispatch queue, and you push it over here and say, go run asynchronously while I show my spinner to the user. This is important. What you're doing is not. This is important, okay, right? So then we get that back. Cool, okay. So the rest of our code is still running on main. It's basically waiting for the result. This spinner that we're drawing is kind of waiting to hear back and from the network and saying, oh, we got the result. The network returned. We have the data. We can display it now, right? So there's a problem with that. Getting results from that is difficult. Here, we do what would kind of be the intuitive thing to do. We create a function called reminder of message string in time, right? So basically, this is kind of an abstraction for like a network call or something, but what we're doing is we're putting a reminder into the queue to pop back out at us and print something at a later time, right? So, when you start your executable, then after so much time passes, something will print, right? And this is kind of to help us simulate something like a network or calling something really slow, right? But if we want to get that back as a result, right, as a return from this function, okay, well, we can't. Because first of all, there's a single expression in this function right now, which is the dispatch queue, which means this function tries to return the dispatch queue because this dispatch queue.global.async after blah, 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 it actually returns a type that you can then reference and cancel and do all sorts of stuff to. It returns an instance of dispatch of the task or the work item or whatever. So this is trying to return a work item, and it's like, oh, that's not a string, right? Oh, sorry, no, this doesn't return a work item. Sorry, it's void. That's what that is. It's an empty type. Basically, it's like, hey, you only have one line here, and it's doing something, but it's not returning anything. You need to return something. And then in here, we try to return something, but because we're within a closure, that return keyword gets kind of captured by the closure, right? The closure says, oh, this return keyword is within me. They're talking to me now, right? The reality is that we're not trying to talk to the closure, but there's no way for us to really talk outside of the closure, right? You can't return for something outside of a closure, especially if that closure is running later, right? So we get these two errors, cannot convert expression, blah, 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 and cannot convert value of type string to closure result type void, because this closure does not expect a return, it expects a return of void. And here we're trying to return string in the closure, right? So this is how you would expect it to be able to work, kind of intuitively, the way that we've written code before. It's not how it works, unfortunately. The way that we have to do this with dispatch queue is by using more closures, okay? So we start to get into this escaping closure thing, because dispatch queue closures that you pass to a dispatch queue, are always escaping, okay? Any closure you pass to a dispatch queue is escaping because it gets held onto in memory and it gets reused and scheduled and it can be messed around with and it gets retained, right, by the dispatch queue. So that means if we try to get a return type back, right, by passing in a closure to it, okay, so rather than getting a return from our function here, instead we take in a closure that we can pass a string to. So we're basically telling the caller of reminder, hey, if you give me a piece of code, I will give that code a string, right? Which is kind of like returning a string, kind of. It's not exactly like it, but it's similar, right? It lets us do this, right? It lets us here, when we call reminder of second reminder in 3, then we get this, closure parameter, right? Reminder in, and then we can print it, okay? So second reminder comes back to us in 3 seconds here, right? And it's been changed, right? It's been changed to have this after time message thing, right? And so after 3 seconds, this piece of code runs, right? But again, because any closure that you pass and use in a dispatch queue async call is escaping, that means this closure needs to be escaping, which is why we learned what escaping was, okay? So this is basically how you get results back from things like network calls, from things like database calls, anything that you need to get a result back from something that's going to run slowly by the definition of a computer, aka more than like 100 nanoseconds or whatever, right? Then you'll use a closure, right? That is the current pattern of how to do things in Grand Central Dispatch. You return by closure rather than actually returning by return type. The problem is, if you return by closure, it can be very difficult to get that return value back to the main thread. Basically, here we have this, thing here, and we're printing it. Now we're adding this thread.current just so we can see what thread we're running on. Well, this closure is now running on, inside of this closure, right? This dispatch queue calls this closure, which means that this thread that this dispatch queue is running on, which is thread 2, then calls this closure, right, which is not asynchronous. It just schedules this onto its own thread, right, which is thread 2. So if we ever need to get access to this piece of code, this string here outside of that thread back on the main thread, we can't. There's no way for us to really wait and get it back. We instead just have to put all of the code that we want to use it with inside of this thread, right? Because if you declared a variable out here or something like that, and then you tried to assign to it inside of this closure afterwards, then by that point in time, that variable has gone out of scope, right? It doesn't exist anymore, because the execution outside of reminder has continued forward while this has been, firing off, right? Okay, any questions about the problem about getting return values back to the main queue? Cool, okay. So you also have a problem of thread explosions. This is that kind of thrashing thing I was talking about. Here, we do this fun thing where we don't realize that reminder of blank in blank is creating a queue every single time. We assume that the person who wrote this function did a good job and reused the same queue. They didn't. They made a new queue every time the function gets called, which means every time a new queue gets spun up, it looks around and says, I need a thread to be running on, so I'm just going to take one from the pool, and if one doesn't exist, I'll make a new thread, right? So if we call this reminder of blah, 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 within for 1,000 times, right? Just one after the other, right? So just calling them as fast as we can on the main thread. It's spinning up new queues and threads as we go, right? Now, it is so fast to execute this print thread.current here. It's a pretty quick thing, pretty quick payload for the thread to print. So as soon as that, thread is done printing that, then it's back in the pool and available to be reused again, right? But we can see here in these, things, there's going to be 996 print statements, and then at the very end, we can see, and actually earlier there's some that are a little bit higher too, but the highest thread that we're seeing being used at this point is thread 66, right? So our thread pool has expanded from your standard 10 to 66 just from this one function call that's being done inside of this for loop. This is why you have to be very careful, and you want to try and avoid using dispatchqueue.global.async if you can, right? You want to use your own queue. Any question about thread explosions? They're also dangerous. Dispatch queues are very dangerous. It's hard to use them safely. Let's take a look at this very simple class A. It has an array of integers repeating from 0 to 1,000. Sorry, not repeating from 0 to 1, repeating 0 1,000 times. So it's an array of size 1,000 and every value inside of it is 0, okay? Then here, we'll create a new instance of A, which immediately has this value. Then outside of A, we will create another one that has the value 1 1,000 times, right? Now, let's say that we want to, send this dispatch queue global async a.array.append contents of new values. Basically, let's say we want to modify this array and add all this 1,000 ones onto it, right? Now let's say we decide we actually, we want to do that twice, but it's going to take a long time. It's 1,000 values, right? We don't want to wait for that, right? So we're going to just do it at the same time, okay? So, we've got this array here. It's a big block of memory. We're just going to add to it on 2 different threads. When 2 different threads access the same exact memory, because memory is not partitioned by thread, it's accessible to all the threads. All the threads in your program can access it, right? Your active memory. If you have 2 different threads accessing the same memory at the same time, writing to the same memory at the same time, or writing to and reading from, if they're both reading, it's okay. But if one of them is writing at minimum, you get a crash. It can look like this. It can look like exec bad access. It can look like any number of things depending on the exact situation. But your program will crash if any threads are trying to access the same memory simultaneously, assuming at least one of them is writing to that memory, okay? Cool. Anyone have questions about why dispatch queue is dangerous and threads are dangerous? All right. So here we have this really, really long set of things, and this is kind of, it's you know, there's a lot going on here, but basically we're pretending that we're hitting a website, fetching a bunch of values, or sorry, a bunch of values, right? Fetching a bunch of values from a website, doing a long running task on them, like, you know, doing a big long computation or running an ML model or saving them to the disk or whatever, and then uploading a result from that computation back to the server. All things that you would expect to take a long time to do, okay? So we're looking at those things and we're saying, oh, you know, we should probably do them all asynchronously, right? We should do them off of the main thread. They shouldn't block. We should be able to continue to draw things and let the user interact and everything while we do this in the background, okay? So you create this to-do queue called dispatch queue label com.todo. We reuse that every time to avoid running into some of those issues that we were talking about. And then we have this fetch to-dos. We use the completion at escaping closure style, where we pass the result in as a parameter to the closure. And again, that is how we return a result from a slow call, right? Cool, okay. And we have to mark it as escaping because we're passing it to the dispatch queue's closure, right? So let's assume we've got this. How do we call this, right? What does it look like to call this? Well, it looks like this. This is what it looks like. This is how you chain asynchronous requests one after the other. If you need a bunch of async things to happen, but you need them to run serially, so you need to fetch stuff from the network. Then once you have that stuff, modify it. Then once you have that, save it to disk. Then once you've saved it to disk, upload it. Then once you've uploaded it, share it on Facebook, retweet on Twitter. Don't forget to like and subscribe, right? You do that by doing this nesting thing, right? Where we call fetch to-dos, and then we have a closure. And the closure has the return from fetching as a parameter. Then we can call average completed stars, and we pass that parameter here. We know that by the time we're in this closure, we have access to it. This is only running later because this is happening inside of a dispatch queue on the inside, right? And the closure that gets passed in, completion, is only called once that long-running background task has finished. So then we call the same, then we pass to-dos, we get back average, then we pass average to upload, then we get back the server response, and then we print the server response. When you chain asynchronous things like this, you can end up with 15 or more calls in a chain like this. And with these three, it doesn't look so bad. It's kind of cool, it's cute, it's really, really succinct, right? But when you have like 10 or 20 of these nested within inside each other, it can be really, really hard to figure out exactly what's happening. So it's really weird and difficult to understand. And we really would rather just be able to like just get the result and then use the result and then upload the result, right? Like that would be nice, but we can't do that with dispatch queues. It's just not possible. There's a way you can do like dispatch queue groups, and it's all very complicated, and there's technically ways to do it. We're not going to look at that because Swift came up with a better way, and that's what the next part of the class is going to be. I would like to click to the next slide, please. Did my clicker die? Nope. There we go. Just a bunch of dead clicks. Oh, I should have done this before I ranted about it. Oh well. Sometimes I forget what I did with my animations. All right, you get 10 minutes, and then we talk about Swift concurrency, which is the language level support for concurrency that Apple has added in the last 4 years. Yeah, so enjoy your 10 minutes. I'm going to drink a lot of water. And I'm also happy to answer any questions anyone has in this time.